So, hi everyone. Good morning. Hi. It's my pleasure to introduce our speaker today for this week's ACOM seminar, Dr. Romaric Odoulami. Romaric is a climate scientist interested in climate change, risk assessment, adaptation, and mitigation, specifically focusing on Africa. He earned a PhD in climate science and meteorology in 2016 from the Federal University of Technology, Akure, Nigeria. He's currently a researcher at the African Climate and Development Initiative, University of Cape Town, which he joined in 2017 as a postdoc fellow. In 2023, Romaric was benchmarked as a young researcher with the potential to become a globally recognized leader in his research field and receive a high research rating from the South African National Research Foundation from his career stage. In today's seminar, he will talk about Africa's climate response to solar radiation modification. And now I will leave the floor to Romaric.
Good morning, everybody. So, I'm Romaric, and from the University of Cape Town. For those of you who have never been in Cape Town, that's how beautiful the University of Cape Town looks like. So, yeah, so my presentation will be focusing on climate response to solar radiation modification in Africa. And this is a work that we started since 2018, and it's a very big work that is being done in collaboration with many other colleagues. I would like to acknowledge, I won't call their name, but it's good to mention that. So regarding my research focus, my research generally focuses on those 4 points, and can be summarized to those 4 points: climate change attribution and weather and extreme, weather and climate extremes, climate modeling, and also climate intervention. So my presentation will basically show you some of the work we have done so far and some data in progress. And I'll show you what we've done, what were the findings, and what were our conclusions. And the very first one I would like to start with is this one that has been published not long ago. And so not long ago, it's focused on drought risk management over the major river basins in Africa. So basically, what we did is to identify major river basins in Africa based on their socioeconomic importance, also based on all the people benefiting from them in a way or another. And now we try to assess how climate geoengineering with stratospheric aerosol injection could impact the characteristic of drought over each of those river basins. And we use 2 different drought indices: SPEI, Standardized Precipitation Evapotranspiration Index, and SPI, which is the Standardized Precipitation Index to characterize drought. So, and we look at the frequency, that's the top row. The middle row is the duration of drought, and the severity at the bottom. So, but as you can see, depending on the index you use to define drought, the results are quite different in the future. And we will see it in the coming up, in the slide coming up very clearly. In this slide, it's much clearer. So the red box plot is SPEI, and the green is SPI. So as you could see at the top row, in the first column on the right, on the left, here we have the difference between, that's basically the projected change under RCP 8.5 relative to the present day climate. And what we could see is that SPI tend to have higher frequency of drought compared to SPI, and the same tendency is observed with the other two characteristics, duration and severity. So basically, there is a gap between the two indices. And one possible reason for that is the difference in the two indices. One is specifically based on precipitation. So a slight increase in precipitation might tell us that, oh, there is no drought or less drought, while a decrease in precipitation could say, okay, there is drought. While in the other case, it looks like the difference between precipitation and potential evapotranspiration to compute the index. So the two variables are taken into consideration. So there is that gap between them, and that offer kind of gives the hand to a river basin manager in terms of, or managing agency in terms of ways to mitigate drought impact over the river basin. But when we look at under SAI, for instance, what we see is that that gap between SPEI and SPI is removed. And that happened because under stratospheric aerosol injection scenario, basically the scenario used here, which is the Glenn scenario, what happened is that SPI drought frequency and severity and duration tends to increase, while SPI drought characteristics tends to decrease. And we could see that all along here for all the three characteristics we analyze, both tend to have be in the same range, basically. And what could be the consequences for that? Basically, this is just a schematic illustration of what happens. So basically, we have the SPEI drought, which tends to decrease in frequency, and as the SPI drought, and the SPI drought that tend to increase, and then they give us this situation, basically. And so, so basically that's, as I said a bit earlier, it reduced the march of maneuver of those in charge of managing the river basin. It makes the work much harder for them. So in terms of takeaway messages for this study, we say that while SAI could reduce drought uncertainty, it could also increase the lower limit of projected drought, reducing the opportunity to mitigate the drought risk over the river basins, basically. So the next study focuses on something that really happened over in Cape Town, in the Cape Town region, basically. And it's we call it the Cape Town Day Zero drought. So basically, between 2015 and 2017, there's been a very severe drought in Cape Town and around, and that basically we were about to run out of water from the tap. So our tap were running dry, and so a lot of study has been done on that drought. So we asked ourselves the question, what could happen under geoengineering regarding similar drought events? So that's what we try to answer in this research. So as I was saying, so this study that was from a colleague who investigated that drought event quite a lot, is on how severe was the drought. So he tried to answer that question using data. And these figures show basically station data from station located in where the water reservoir in Cape Town are located. So basically, I think 3 stations which are as far as in the 1930s, and what is showing here, that here we have basically the total annual rainfall, the total annual rainfall, and we could see that 2017 is kind of the driest year in the whole record of over 80 years long. And in the second here, we have a 2 years running mean. So it shows that 2016 and 17 is kind of the second driest in the whole record. But when we move to the 3 years mean, running mean, we notice that 2015, 16, and 17 is basically those 3 years combined represent the driest 3 years in the whole record. So basically the drought happened between 2015 and 2017. It was characterized by a decrease in precipitation. And so those 3 years were quite dry, with 2017 the driest actually of the record. Yeah. So then they fit this data, the 3 years running mean, into a gamma distribution, and this is the histogram, and then try to determine here the return period. And what it shows here is that it shows a return period of about 311 years, and which fit into a 90% range of 105 to 1280. So basically that was the range based on the data used. So it was quite severe event. So we try now to analyze that drought in the context of geoengineering. And for that, basically we use different observation data and try to determine the return period across a different range of observation data, including station data and also some graded observation and reanalysis. And then we find a return period that ranges from about 40, 50 years to about 400 years return period. And then we use the median value of that return period that was around 100 years. So we define our event basically as a 100 years return period, a 100-year event, 1 in a 100-year event. So basically, so that's what it corresponds to in the GLANCE data, the historical, the control run of the GLANCE data over the period 2010 and 2030. So those what it corresponds to basically. And that this horizontal line basically is the event. And that's the corresponding return period in the historical GLANCE data, or the period we use as the present day climate in the GLANCE data. So, and then we see that under RCP 8.5, from 100 years, 1 in 100-year event, it moves to about 1 in about 6 years event basically. So the event is becoming more and more common in the future under a high emission scenario. But with geoengineering, we see that it could bring it back basically to about 75 years, 1 in 75 years event, which is quite closer to what we call the present day climate. So we went a bit further away. As we are using an attribution-based approach, we went a bit further away and determined what is called the fraction of attributable risk, basically. So basically, what is the fraction of risk attributable to climate change or high emission scenario? But in this case, we are also interested to also geoengineering. So when we did the same analysis here, like what we saw in the return period analysis, we noticed that under RCP 8.5 versus the present day climate, the risk of such event could increase by about over 90%, 94% plus. And that could be attributable to high emission scenario, the high emissions in the future. But when we look at SRM versus the present day climate, we see that that risk could be reduced to about 25%. And then we say, okay, let's now compare the two futures, the future with SAI versus the future under high emission scenario. And then we saw a reduction in risk of about 90%, of over 19% actually, which is quite a good, which is quite interesting basically. So basically, SAI could reduce the risk of similar drought in the future by about 90%. So we also try to look at, okay, what are the mechanisms behind this event? So here is a result of trend analysis of the southern annular mode, which is a leading mode of variability in the southern hemisphere. So basically, depending on the science it takes, it tells us the position of the westerlies, which are very important for the Cape Town region. So basically, the Cape Town region is a winter rainfall region. So it receives most of its rainfall in winter. And that depends a lot on the westerly that brings cold front systems around the system. So when those westerly shift to southward, basically we will receive less rainfall over Cape Town. But when they are northward enough, rainfall will be received over the season. So basically we did a trend analysis of the southern annular mode over the different seasons. Generally what we see is that we have a reduction in trends under SAI compared to RCP 8.5, especially in winter where we have a reversal of trend from positive to negative trend, and basically, which is what it means basically, the southward shift, that there was a southward shift, there is a projected southward shift in the mechanisms that bring rainfall over the Western Cape under RCP 8.5. Even in the literature that was reported. So we find the same thing here, but we saw that with SAI, that southward shift could be partially offset, allowing us to receive more rainfall over the region. So so basically, the takeaway message here is that despite the fact that we find a positive result in terms of the impact of SAI on rainfall and drought over the southwestern Cape region, which is the region where the city of Cape Town is, we say that that these results are quite specific to the design of SAI, but also model use, location of the study, etc. And that using different scenarios, etc., could lead to different outcomes, or in different regions, we are expecting to get different results. So this is not enough to recommend SRM as a possible way of reducing the impact of climate change in the future. So the next study is also a local scale study, but this time on a country scale. So we try to understand how SAR could influence extreme precipitation and temperature over South Africa and the implication for vulnerability of the country. So basically, the country is kind of split into different climatic zones, 12 in total. And then we try to see, okay, how would extreme temperature be in the future under SAR? So in the first column on the left, we have basically the present day climate, how those different temperature indices looks like in the present day climate. And in this column, circled in red, we have the projected change in temperature and temperature extremes over South Africa under RCP 8.5 related to the present day climate. And what we could see here is that over the whole country, we have an increase in temperature, which agrees with previous work on projected change in temperature over the country. But with SAI, what we see is that there is a general cooling across the whole country. And in the last column on the right, basically that's the difference between the SAI and the future under RCP 8.5. You could see by how much SAI could offset future warming. And very interesting thing here is that all the ensemble members used here agree on the sign of the change. mostly across the country, as we could see here and also here. But also here, what we see also is that the cooling is quite effective in terms of SAI is capable of offsetting all the warming projected on the RCP 8.5 basically across most parts of the majority of the country. So, but when we come to precipitation, the result is quite more, is more variable, is not uniform. Some regions could experience decrease or increase in precipitation and extreme precipitation. But particularly what I would like to focus on here is this. These regions are projected to have increases in precipitation on the RCP 8.5. But with SAI, we see that most of this precipitation is offset and replaced by more drying, except over this slight region in the east coast of the country. And that region is quite interesting. It corresponds to a region, a province called the KwaZulu-Natal province. There is a coastal city called Durban. And that city is quite vulnerable to extreme precipitation already in the present climate. And the future is projected to be worse. So we could see that SAI is basically going to make it even worse. So basically, exacerbate the already increasing, the projected increase in precipitation extreme over that region of the country. So, and one other thing we need to look at it here is this region, the Southwestern Cape. So in the previous study, I was saying that drought risk was decreased by SAI. So we could see that the region is projected to dry in the future under RCP 8.5. And basically, we have that drying is offset under SAI. That's kind of agree with the previous study we did. Yeah. So, and then we look at the different climatic zones. So this is for temperature, all good. Not much to say there. The cooling is general across across all climatic zones. And sometimes even the cooling is complete or there is overcooling over some other regions. But when it comes to precipitation, it varies according to the region. And so some region could benefit while some others won't. So this is just an example. So this is the Southwestern Cape region, basically, where Cape Town is. So we could see there that most of the precipitation extremes are projected under RCP 8.5 in red to decrease and to decrease, except consecutive dry days, which is increasing, which gives a kind of signal of drying signal also. But under SAI, we could see that some of that decrease in precipitation is offset and replaced with more rain. But over the KwaZulu-Natal coast, which is basically the region I was talking about a bit earlier, we see that those regions was projected to experience increases in extreme precipitation, and that is going to be exacerbated under SAI, basically. So that region could become more vulnerable to flooding and etc. So, but the most important thing we did in this study is kind of a brief summary of this study, the vulnerability implication of those changes. So basically what we did, we used the literature to try to understand what are the projected changes on the RCP 8.5, what could be the implication of that change, and what is the impact of SAI and the implication. So basically, so when we take this, take the top, so we could see that the decrease in precipitation over a region will be associated with decreased water availability, but that could be exacerbated under SAI. For instance, when we take the KwaZulu-Natal coast region, climatic zones, and that could even induce more drier, decrease in precipitation under RCP 8.5 will be associated with decrease in water availability, and SAR could make it even much worse and exacerbate the drying condition and reduce more the water availability. So in the health sector, for instance, so when you take increased hot extremes under RCP 8.5, that could be associated with increased heat stress and disease, some disease outbreak, etc. But with SAI, could be a decrease in hot days, and that could increase a cooling effect and reduce the heat-related morbidity and improve mental health, etc., etc. So, So similar for some other indices. So basically, this is a way for us to see, okay, what could be the implication of this finding for society? And that could also be useful for policymakers, etc. So in conclusion, what we could say is that SAI may have beneficial outcome in one region of South Africa, but deleterious outcome in another. So we recommend more research to kind of further investigate the different scale on which this analysis could be done, etc. So this work is basically, it's not focused on Africa, it's global. And basically what we did here is trying to see, actually it's still in development, just some preliminary results. So basically is to try to see, quantify the impact of stratospheric aerosol geoengineering on biodiversity exposure. So this figure, what it's showing basically is the risk of species loss. So we could see under a 1.5 warming level scenario towards 4.0 degree warming scenario, and you could clearly see that the increase in terms of species loss is increasing as the warming level increases. In a previous study, what we did was trying to quantify, to look at species exposure under temperature overshoot scenarios. And what we could see here is, so here it's marine species. In black, we have terrestrial species, and the red is temperature. So basically, when we have a temperature overshoot, we could see that even after mitigations, scenarios, etc., to reduce warming, temperature doesn't come back to what it was before the overshoot, even up to 2300, year 2300. So basically, a similar thing is observed with the population exposure, the global population exposure for both marine and terrestrial species. So, and this is the maximum exposure that we found that some species in some region could be, all species in some region could be highly exposed to dangerous temperature, especially across the equatorial regions. So, this study tends to assess the potential of stratospheric aerosol geoengineering to influence the exposure risk of terrestrial vertebrates to potentially unsafe temperature in the future. So basically, we use the GeoMIP scenario here, and most of us know how the GeoMIP works, but briefly, basically SO2 is injected into the stratosphere near the equatorial region from 2020 to reduce the radiative forcing under SSP 8.5 to the SSP 245 level, basically. And we use the different scenario available under CMIP and GeoMIP, GC sulfur. So what the data we use comprises over 26,000 species, vertebrates, terrestrial vertebrates, that include amphibians, birds, mammals, and reptiles. And that's where the source of the data, basically. So the method we use, so we basically determine the realized thermal niche, which is basically, so we're using the historical climate from 1852 for each species. And so basically, that's the realized thermal niche corresponds to that, the historical temperature. And then we have the realized niche limit, which is basically the maximum temperature over that period. Maximum mean, basically the annual mean temperature over that period. And then exposed species in the future. So basically, we say that a species is exposed in the future when for 5 consecutive years we have temperature that exceeds the realized niche limit. So whenever we have in the future temperature that exceeds the maximum historical temperature for at least 5 years, we say that the species has been exposed. And the de-exposed species is a species after being exposed experience 5 consecutive years below the realized niche limit temperature, basically. So then let's assume that the yellow or orange part shaded area on the map is where we have our species. So basically, we try to determine in each grade the exposure year. So basically, the estimated realized thermal niche for each species based on the data we have. So we graded basically the data in 1 degree by 1 degree to make this. So each grade is considered as an assemblage, basically. So basically, we will determine for all species exposed in this area, okay, what's the year of exposure, and then we move on to determine the magnitude of exposure, etc. So in terms of magnitude of exposure, we define it as the percentage of species exposed at a given site, and the abruptness is the percentage of species exposed in the decade with maximum exposure, and the timing of exposure is the median year in which the exposure occurs. So in terms of results, so this is the magnitude of exposure, and what we see is in red, the red color bar here basically tell us we have higher exposure under GC sulfur under SAI, and the blue under SSP 245. And what we can say is that there are some very important regions, especially where we have the tropical rainforest, the Amazonia, and also the Congo Basin region, where we have places where, those are places where we see that SAI is very likely to induce a very high exposure, under a very high species exposure in the future. So this is showing the cumulative exposure over time, and we could see that under GC sulfur, basically, you have a slightly higher exposure compared to SSP 245. So that's, in terms of population exposed. So this is basically the top 10 in terms of higher exposure, and top 10 in terms of higher exposure, in terms of countries, basically. So this is showing in red, those are the countries where higher exposures under geoengineering are very likely to happen. And in blue, countries where higher exposure are likely to happen under SSP 245. So basically, we could see that some countries, especially in the tropical regions, are kind of, especially we see Congo and some southern American countries that are part of the Amazon basins are going to experience a very high exposure under SAI compared to SSP245. So this is the timing of exposure. So here there is a bit of a shift in the color bar. So the blue here indicates that we will have early exposure under SAI basically, and the red under SSP245. So, and regarding the abruptness of exposure, you could see abrupt exposure, which is much more geographically spread under GC sulfur or SAI compared to SSP245, especially in regions that are very with a very large diversity of species in the Amazon basins or in the African rainforest region, and also in, yes, this region is Southeast Asia. Good, yeah. So in terms of take-home messages, we say that lower exposure to potentially dangerous temperatures so basically what we did, we see that there are lower exposure to dangerous temperature under GC sulfur compared to SSP245 generally, but we could see that about 14% more species could be exposed, species exposed under GC sulfur than under SSP245, with the highest exposure projected over the tropical forest in Brazil, the DRC, and Indonesia, Colombia, etc. So in the Sahelian region, however, we see that less exposure under GC sulfur, especially the Sahelian countries, Mali, Sudan, South Sudan, etc. And also, despite the fact that GC sulfur has the potential to reduce species exposure, we notice that it's still possible to achieve lower exposure under SSP245 compared to SAI when we consider the scenario used in this study. So, and then we say that in the context of this study, it's important to point out that cutting emissions remains the best way to prevent ecological disruption. And also, so developing, based on the finding of this study, we could see that developing countries tend to be the most impacted in terms of species, in terms of benefit and feedback and side effect of geoengineering on the species. So now the last part of this presentation is about the Simons grant that we got, and that basically brings me here to collaborate with Simon. So basically, briefly, the research tends to basically look at the global and regional climate response to stratospheric aerosol injection using different materials in addition to the sulfate-based materials. So the point is to assess the potential impact on the climate and the driving mechanisms of those changes observed in the climate or projected in the climate, and then explore the implication of those changes to agricultural biodiversity, but also energy, renewable energy, water resources across Africa. So basically, this is the workflow of the study. So we have 4 aims, and each aim is attached to one work package, one in climate modeling and climate model development, where we're looking very much forward to collaborate with Simon and her team, and also looking at the global and regional climate response to alternative materials. And the third one is mostly on what could be the implication of changes in the climate to key sectors of activities in terms of like agriculture, water resources, energy, and biodiversity in Africa. And then trying to quantify the risks associated with SRM and within the attribution framework. So we got a quite big team with this funding. So we got a total of 26 researchers, including 8 postgrad students. So 6 of them will be based at the University of Cape Town and 2 at the University of Nairobi in Kenya. And about 10 African countries so are involved in this research. So basically the researchers are from their country of origin, basically, from different 10 African countries. Of course, we got a Brazilian, but he's already in South Africa, based in South Africa, working with us. So that's Brazil is the 11 countries involved, although it's not an African country. But we are collaborating also with Simon's team, but also with Timofey's team in the Sweden. They're also a Swiss team, and also a colleague, Alima Dajuma from Côte d'Ivoire, who is bringing her expertise in terms of heat wave analysis. She has developed a lot of expertise in that area across the African continent. So basically, that's it. So those are the African countries that are represented in the project. And we'd like to acknowledge some of the funders of the research I've presented. Firstly, Simon's Foundations that provide us with the largest funding in the Global South, focusing on climate geoengineering research, but also the Carnegie Corporation of New York and the Great Initiative, the National Research Foundation in South Africa, who are the main funding organization. And also acknowledge all of my colleagues who have contributed to the research I've presented to you here. Thank you very much for your attention. We really appreciate your comments, suggestions, and questions if you have any. Thank you very much.
Thank you for the presentation. For people watching online, you can type your question in the box below the video, I think. And for people in the room, we're gonna try something new today. We're gonna use this catch box to, because it's hard to just hand over the mic. So just whoever raised a hand, I'm gonna just throw this to you, and you can just speak to this.
Hi, thanks for the great talk. I have a question about the first part of your presentation, because I always heard that taking SPEI is better because it's like the real drying, but on the other hand, it's a lot harder to measure because it's hard to measure evaporation. So I was wondering, what are your thoughts about that?
Yeah. Potential evapotranspiration can be a nightmare to calculate it. Required sometimes too much variables that we can't always get from the model. But in our case, we use an approach that allows us to calculate the evapotranspiration without too much stress. So I think we use the second. I can't remember the approach we used, but it wasn't the Penman and Montet. That's the most complicated. The second most complicated, that's the one we used. I can't remember the third one. But so we use that approach to calculate it. It requires us to use, I think, minimum and maximum temperature to calculate it. So that's what we did. And the result were quite okay, but yeah, I guess if we have been able to calculate the most complex approach, maybe the result will be much better. I don't know, but basically we do with what we have. Basically, yeah.
Thank you.
Hi, yes, thank you for the talk. So I'm not familiar with all the different scenarios, the climate scenarios, but you showed a temperature going up and then going down again and stabilizing. And I'm wondering if you could describe to us how that is achieved.
Oh. So this was the overshoot scenario. Yeah. That was the overshoot scenario. So in semipsis, it's basically a scenario in which the allowed temperature increases following, I think, SSP 8.5, which is the highest emission scenario, basically. And so, and until, I can't remember exactly which year, from that year, aggressive mitigation approaches has been implemented to reach a certain a net zero by a certain target period, basically. So that's why you see temperatures start decreasing after the implementation of the aggressive mitigation scenarios.
So would that be from methane reductions then?
Yeah, it's I think CDR mostly, and I think.
So renewables included in those scenarios.
Yeah.
So they pull out actively CO2, but
I
also
see.
all the emissions go down.
Down, and reduction of emissions also,
Yeah.
basically.
Thank you.
I have a question again to the Cape Town day zero, but also when you showed you showed the regional changes in rainfall and temperature, and it's quite well resolved, the differences. And could you explain how with the climate model, you get geoengineering output in 100 kilometers. So you apply some kind of downscaling for this?
No,
This is right out of the climate
that's
model?
the raw model output we analyze.
Yeah.
Yeah.
So
No
if we
downscaling.
do apply regional refinement, like we're planning to do maybe a 25-kilometer grid, you could maybe potentially get very different answers, you think?
Yeah, I assume so. But the good thing here is that already at such a coarse resolution, you could see how diversified the impact is across the country. So I assume that if we go at a much higher resolution, we will get quite amazing details that are, for the moment, escaping to our attention. So, yeah.
Yeah, this is a really interesting presentation, and I'm curious, thinking about these results that you presented in the first part, there seems to be big trade-offs, right? So you get benefits in temperature, but not so much in precipitation, right? So these are hard decisions. And trying to connect that to the last part of your talk, do some of these mixed results potentially change with materials other than sulfate, or is that just not a connection to be made?
That's a complicated question.
I'm good at that, sorry.
So I'm not sure it will change much of the results. However, one issue with sulfate aerosols is their negative impact, not just as the result we are looking at, the negative part of the result I presented, but also they have negative implication for health, but also for the ozone layers, etc. So, and if a material could be used to replace or to, instead of sulfate aerosol on which people have focused for the last couple of decades or so, because the idea was coming from basically from volcanic eruptions. So I guess people look at it in the context of volcanic eruption where we have sulfate aerosol being ejected and reaching the stratosphere. So basically that would be, but it's obvious that sulfate aerosol have negative implication for the environment, for human health, but also for many other stuff. So that was the motivation of the study, of the proposal we wrote to get this funding. And so we would like to see if the impact on the climate would be any different from what we see with sulfate aerosol. So.
More questions? Well, if not, then let's thank the speaker again. Thank you for the great presentation, and you'll be visiting ACOM for
1 more week.
yeah, so he's around to discuss more. Okay, see you all in the week after Thanksgiving.